All right, so once again, my name is Damon Tordini, and I'm the product manager for flow simulation and plastics. With me is Team Milo, the product manager for SIMULIA Abaqus, and this is going to be an overview of simulating various manufacturing processes with the tools and services that we offer from Hawkridge Systems. If you're not familiar, Hawkridge Systems is a provider of engineering, design, and manufacturing solutions, and among those would be analysis tools, of course, meant to be used as part of the design process. And we have a pretty robust team here with a wide range of experience in different tools, and so we can likely help you, no matter what industry you're in or what your requirements are. If you're trying to design a product and make sure it operates well, or if you're trying to design some tooling or simulate the manufacturing of a product to make sure that it comes out the way you expect it to in the first place. So among all of the things that we provide, from design tools to data management, 3D printers and whatnot, the simulation tools generally fall into kind of two main categories. We sell and support the full line of SOLIDWORKS analysis tools, so that would be SOLIDWORKS simulation, flow simulation, plastics, different kinds of stress analysis, as well as what we call SIMULIA Abaqus, which is a dedicated sort of high-end analysts tool, which could do some very complex multi-physics problems, extreme deformation, and some other capabilities that Tim is going to talk about. So, like I said, we've got pretty wide range of experience, and we're going to try to give you an overview of which tools can do which types of problems, where the sort of boundary is, where the cutoff is, and we've got a good amount of experience in different processes from different types of companies where we think we can recommend the best way to go or the best workflow for whatever you're looking to accomplish. We have a lot of experience training users of all types to use these tools as well, whether you've got a lot of experience in FEA from your school background or previous job, or if you really have never used simulation at all and you just kind of used to designing in SOLIDWORKS, we can make sure that you're doing things in the most efficient way possible. You're using sort of the most integrated solution, and so that's one of the benefits of working with us, is that we're kind of a one-stop shop. You won't have to reach out to different companies because you're trying to make, just because you're trying to make different softwares work together. And we can provide everything from support to training to mentoring for all these products. So again, we're going to be talking about most of what you see on the screen here: SOLIDWORKS simulation, SOLIDWORKS flow simulation and plastics, and SIMULIA Abaqus. We're going to start with more of a structural approach to a manufacturing problem. And so in a lot of these cases, whether you're designing a product or trying to predict how it will be manufactured and design the tooling, there's probably a process you go through to sort of ramp up your knowledge and obviously nail down the aspects of the design more clearly. And we go through our own process, of course, when we're trying to help you guys do the same thing, whether we're trying to get you the skills you need to run a particular type of analysis. Of course, we provide everything from blogs and videos on our website to technical support, training classes, and even full-on analysis consulting. But anytime we approach something like a customized training or mentoring or consulting job, we kind of follow this process of getting the information from you about what the requirements are and what the variables are that you might want to change, how realistic you want to make things, and of course all of those details. And so a big part of that discussion is figuring out what the capabilities are that you need to get a particular result. And so depending on how far you want to go, we might recommend different tools. And so even in the same process, even in the same manufacturing or design process, you might want to use different tools depending on what stage you're at, even if you're talking solely about analysis. So one example of that would be a cold work beam, where maybe you've got like a C channel as what we've got here, where you want to simulate the manufacturing process of that beam, and then maybe also what happens when you load it after it's been manufactured. So as you probably are aware, simulating permanent deformation, like forming a piece of metal into its final shape from a flat, or loading it in that situation, that's a pretty advanced type of analysis, and it's something beyond what just a basic static stress analysis can do, which many of you may have used in the past. And so at a minimum, if you wanted to approach this type of a manufacturing problem, and most likely any type of manufacturing problem, because it involves permanent deformation to a material, you're likely going to, at a minimum, need what we call a nonlinear study, which is part of SOLIDWORKS Simulation Premium. That's the sort of top-end SOLIDWORKS simulation package if we're talking about FEA tools. So the nonlinear stress analysis allows you to put in the material models, the contact definition that you would need for any kind of a manufacturing problem like this, and it also has the contact detection abilities beyond just a simple static study that you would need. But even the nonlinear study is going to have some limitations. So let's try to see how far we could get with SOLIDWORKS simulation. So I'm going to pop open SOLIDWORKS here. And here's a simple model that we whipped up of sort of the forming process. If I go sort of back to the default version of this, basically what we've got is a die and sort of a base block and just a flat piece of metal that we've modeled up between them. So obviously I want to bring this die down, and that's going to help me form that C channel as, of course, the two parts press the metal plate into the shape between them. So I would, of course, turn on the SOLIDWORKS simulation add-in to do that. But as you probably imagine, this is a very complex type of analysis, which could take a long time to run and would require some pretty particular inputs, things like the right material model. And as far as SOLIDWORKS simulation goes, the nonlinear solver, the nonlinear version of the Cosmos solver to be specific, it can do a lot for what it is, but it does have some limitations. And one of the issues with the Cosmos solver is that sometimes if there is buckling, especially buckling in a contact problem like this, can be difficult for the solver to get over. And also the solve times can be challenging if it's a much more detailed mesh. So if I wanted to simulate this full beam, for example, at the right level of mesh detail to really see what's happening in those bends, it's going to take a while to solve. So most of the time what we recommend is using what we call 2D approach. We can do something called 2D simplification to simplify the problem greatly and make it much more practical to run and much faster. And so we would go create a new study, specifically a nonlinear study, and use this 2D simplification option. So that's what I've done here. If you take a look, basically I've created another configuration of this model where I cut it in half, and that way it'll solve much faster as well, because we're going to take advantage of symmetry. And the 2D aspect of the simulation will make it solve much more quickly. And it'll also remove a lot of the questions of, what type of mesh elements should I use, shells versus solids or things like that, which can be a big part of the setup process. So in this case, I've got my materials defined, of course. One of the nice things about SOLIDWORKS is the built-in library. So I've got things like 316 stainless steel sheet defined already in the database with the right plasticity model. And you can see here I've also got my contacts defined. So that's the no penetration contact between the different parts in purple there. So of course that's going to give me the right kind of forces between the parts as this base moves down, which has also been specified here. You can see there's a fixture, or in this case it's a reference geometry restraint that's going to just move it downwards about 1.5 inches. And that's the distance in this case, the vertical distance there to form that beam. And so if I were to mesh this, in this case you can see that one of the benefits of the 2D simplification is you can have really detailed mesh even in something like the beam here where I'm looking at the cross section of it, and it'll still run in a reasonable amount of time. So this particular one ran in, I think, about 3 to 4 minutes here. Looks like it did, and of course it would do all its calculation steps that are necessary to see what the stress and strain and displacement are at all these different stages as the die is moving down, and of course we'd be left with an animation, and as well as all the numerical results about what's happening during this process. So we can see there, of course, the channel mostly gets formed at the beginning there, and then as you would expect, stresses are developed over time. which of course will be beyond the yield stress in this case, which means it's going to be permanently formed into that shape. And one thing you might want to do in SOLIDWORKS simulation, probably the limit of what you could get out of this, is figuring out if the metal is going to be formed like you expect it to, and if it's going to break. So one thing you could do is to look at a strain plot and just make sure that you're not exceeding the maximum strain of the material. In this case, this steel has a maximum strain of like 4.5%, so we would just take a quick look as we're animating and make sure that we're not exceeding that, which in this case, we might be in one spot. So maybe we'd need to adjust the material that we're going to use, or or the thickness of the plate, or some of the other aspects of the design here. And if you want, there is a way to view this as if it was a full 3D model as well. But again, it's only going to kind of visually draw the results down as if it looked like the original 3D model. This is still a 2D simplification. So obviously, we're talking about a few limitations to what we can get out of this type of analysis, right? We had to go with a 2D simplification to get a reasonable solve time. We really can only simulate the forming process and not subsequently, putting the load on the real 3D shape to see what those manufacturing stresses do. And also something you should be aware of is that there are some problems where the Cosmos solver in SOLIDWORKS simulation has more difficulty getting the resolution that you want and the solve time that you want versus something like SIMULIA Abaqus. So this is where I'm going to pass it over to my counterpart, Tim Milo, who's going to let us take a look at how you would do the same type of problem and how much further you could go if you're using SIMULIA Abaqus to do the manufacturing process that we just looked at and the subsequent loading.
Yeah, thanks for the introduction, Damon. Hello, everyone. I'm Tim Milo. I handle the Abaqus product and our analysis consulting team. And I want to go through some of the areas where SIMULIA has kind of a strong point in these analyses where we go through forming and self-contact. You can see in the example in the center of the screen with the collapsing tower that we've got a lot of areas where we have quite a bit of deformation and self-contact as that buckling occurs, and a pretty nice match to the physical test on the right for that energy barrier. And we have a few different types of multi-physics we can get at with SIMULIA Abaqus. On the far left, we have an example of a cell phone, which we can see the cracks running in the glass through a process of reducing the shear stress, which is part of having a few different failure criteria built into the material models. And then last, just want to touch on, we have some ways to represent fluids in these in the collapsing water bottle that you see in the middle, and the tire example on the right. It's used across quite a few different energy industries, and I think the main takeaway here is that a pretty robust contact algorithm with a big variety of material models makes it something that is highly customizable to your application. So you do see specialists get very deep into the physics across all of these industries. And so it fits in with our analysis suite package, basically picks up where Simulation Premium stops, most of the same analytical capabilities, and we have the ability to co-simulate with, couple with other CFD codes. There's not a CFD code built in directly to Abaqus, but it does partner with quite a few different CFD codes in co-simulation. So I'm going to get into setting up the same basic problem that Damon went through, and I'll touch quickly on a few of these different options in terms of pulling the geometry in, what some of our material options are for setup, and where when we choose our study type, we have some choices there that kind of dictate the type of results that we can get at. Here's the beam forming. In this one, I show just half of the beam so you can see the fixture and the beam as it forms. And the key result that we're after here is we want to compare what happens if we consider the cold work or if we do not consider the cold work. So the beam on the far left is annealed after formation. The beam in the middle is not, so it starts with some strain hardening along the beam edges. And you can see there's a bit of a different response where if your priority is to get the maximum load, typically you'll have a peak displacement at a peak load, and you can take some fraction of that as your design load for, say, for earthquake resistance. So in the case of the cold work beam, even though it reaches a lower peak before it has some local instabilities, if you take a fractional amount of that displacement and pick a load, typically it'll handle a higher force at any given displacement than the annealed beam, and so that one's actually better for a lot of applications. First, I'll just quickly touch on the material model, which is we just use the structural steel with 50 KSI yield, and we put an annealing temperature to it. And now I'm going to start in the software to show you how some of these choices are made. We have a quasi-static run, which means it's a dynamic analysis, but we're really only concerned with internal and inertial force, or internal stiffness, and not necessarily inertial forces. And then one thing I'm going to highlight is that we did an annealing step, or we omitted that step to either consider strain hardening or not. So now I'm going to pull up the CAD model and go through the workflow of pulling that into Abaqus. So you can see on the left, I've got the same sort of basic beam setup that Damon covered. On the right, we have our Abaqus interface. Our models are organized in trees. So as we look at the model tree, we start with parts, work down through material properties and everything else. So I'm going to bring this into Abaqus using the associative interface. So we set a temp directory and we pull that over. And now that we have the CAD in Abaqus, you can see we have the same assembly, same part names, and then those are called instances when they're used in the assembly. So I've gone through some of the steps to set this up ahead of time, and so what I want to show you now is the way that the components are meshed. Typically, we'll use sort of a coarse hex mesh on the pieces that aren't key to the analysis, and a much finer mesh on the plate. So the parts are considered are discrete rigid parts, which means that they don't add much computational time to the analysis, but they are simply meshed so that we can capture their surface. We also have several distinct steps through the analysis, which is kind of a unique thing to Abaqus versus some of the other tools. So I have a step called form, remove, anneal, and settle. Now, if we go in to look at our boundary conditions throughout those steps, we have some things that are turned on and turned off throughout. Basically, what we're going to do is we're going to move the backing plate in for that first forming step, and then we're going to pull away the fixture in a second step. The anneal step, all that does is set the temperature to reset the stress state, and last we have a settling step where we're going to import it to the bend test analysis. So first I'll go over into the formation results and just show you what that looks like if we animate that. We have some options. We can hide different parts of this as we show it, and I can color these by separate parts, as well as hide the mesh so we get a cleaner picture of what the key pieces of interest look like. So I'm going to go ahead and hide the anvil and the base and just leave the plate so we can sort of see how that gets formed. So the key here is at the end of the analysis, the plastic strain is removed. So if I go to the very beginning, there's no strain on the part. And as we work through this analysis, we get some higher concentrations of strain, and then it's in yield. So that's our start point for the loading tests that I go on to do in the displaced beam. So you'll notice here I just have a flat plate. One of the things that we do is we go into the load condition and we read the results from the forming state. The loads for this are pretty simple. I import it and then I displace it to the right 10 or 12 inches, something like that. So if we come in and look at this result, we start in the initial condition from the end of the other analysis where we're looking at the cold work model here. And we just drive that until it gets some pretty severe distortion and local buckling. This is the one that had a lower capacity, so basically started to buckle sooner. And if we plot, we can track any of the that type of data side by side. So here I'm going to plot what the reaction force versus displacement looks like, and that's kind of how we arrive at the difference between the two. Is we can just go in and mine those type of results. They both, are pretty severely distorted, but it just happens earlier with the cold worked beam at a higher load sooner. Which, if you're measuring to a narrow allowed displacement, that's an ideal situation for a beam like that. So going on from the beam analysis, I'll give it back to Damon, and we've got one more type of analysis to touch on.
Yeah, thanks, Tim. So yeah, just to sum up where we were, basically we looked at how SOLIDWORKS simulation could more or less just predict what sort of the plastic strains were in the channel after we formed it, but SIMULIA Abaqus can take us much further than that, looking at different annealing processes, what the sort of residual stresses are in the material, and then once we load it, how that affects things like buckling or the amount of load that, the peak load that it can handle. So that's kind of a similar theme. The SOLIDWORKS simulation tools generally will have a quicker setup time, and they'll be able to make some of the assumptions for you to get you started pretty quickly, but you're definitely going to run into some limitations in depending on what you're looking to do, and SIMULIA Abaqus usually allows you to go much further and customize things in a lot more detail as well. Another example of that would be a blow molding simulation. This is really something that probably can't be approached at all in SOLIDWORKS simulation. But if you were trying to simulate something like maybe a plastic bottle or any other kind of object that's molded by shooting pressure in through a thin, plastic or polymer sheet, SIMULIA Abaqus can handle the large amount of deformation required to predict that and the complex contact between the plastic sheet and the surrounding die. And it even has the ability to define the right kind of sort of internal pressure loading that would be causing the expansion, causing the actual blow. So again, this would allow me to simulate that large amount of deformation, figure out what the sort of final shape of the bottle is, and if it has the right kind of temperatures and other properties when it comes out. And you can see right there, by the way, that that animation is showing this same simulation being done not in the SIMULIA Abaqus desktop program, but in something called 3D Experience, which is sort of the online cloud-based alternative to the same technology. So diving further into this realm of more like plastic manufacturing processes, another example that we can take a look at would be an extruder. If you're familiar with things like laminate flooring, or really any kind of plastic structural piece that might be part of furniture or anything else, these are often made through extrusion processes where you've got a die, of course, that has a continuous stream of molten material that's flowing through it, and then of course there's probably another mechanism that comes along and chops it off at the right time to give you an actual piece, an actual member. So this would be another case where we can get you part of the way with SOLIDWORKS analysis tools, and specifically in this case we're talking about SOLIDWORKS flow simulation. This was for a customer whose primary concern was trying to make sure that the molten material was coming out of the die at the right temperature, and based on that they could you know, predict that it's going to cool properly and allow them to cut it at the right time. But a big part of that, the question when they were designing this tooling was, you know, what kind of a cooling setup do we need? Do we need cooling lines, or what should the kind of gap spacing between you know, sort of the inner die itself need to be, so that we get the right thickness of the material and all of that type of thing. This is for like PVC pipe, actually not flooring. So with SOLIDWORKS flow simulation, we can predict, first of all, we can simulate a non-Newtonian fluid, which is what most molten plastics are, molten polymers. So we can simulate those, and we can predict the flow rate and the velocities in the fluid, the temperatures in the fluid, the shear stress, which again may be important depending on how the material cools. And so while, you know, when we use SOLIDWORKS flow simulation, because it's kind of this general purpose tool that's got some useful capabilities in all industries, we can get at least a good chunk of the data that we would need to make this kind of an estimate. Just so you're aware, there are some add-on modules for SOLIDWORKS flow simulation, although in this particular case they wouldn't be necessary. And so this customer ended up using the software, as you can see there on the right, to confirm that the die temperatures were as they expected, and that of course the velocity vectors of the molten plastic were correct as they were coming out. And while you could go a little bit further than this with SIMULIA Abaqus and potentially simulate sort of the extruded material coming out itself, Abaqus really would not be able to give you the complex kind of thermodynamic behavior and fluid behavior of what the molten plastic is doing inside the die like this. So this is kind of an area of specialty for flow simulation, especially compared to how easy this tool is to use. And obviously you can get all the results you would want, like the streamlines and cut plots and surface plots, and very intuitive for most, you know, SOLIDWORKS users to pick up. And let's look at one final case, also still in the realm of polymers or plastic manufacturing, and that would be, of course, be injection molding. This is probably, as you're maybe aware, the most common type of manufacturing for plastic components. Probably about 80% of plastic parts is the number I've heard. And so again, this is a pretty complex process involving heat transfer inside an injection mold and non-Newtonian properties for the fluids, as we just talked about, and phase change. Of course, if you want to know, what a final part looks like, you not only have to simulate how the molten material flows around inside an injection mold, but also what happens when it cools into the final shape. And so because those physics are particularly complex, and this is kind of a niche industry, SOLIDWORKS Plastics was created as a separate product specifically to address that. So this is kind of different from the other simulation tools, which are all more of a general purpose. This is very specific. It's meant for one type of process only, but it simulates all aspects of that process. It simulates the fill of an injection mold, filling up the cavities and runner system, the packing of that mold, which basically helps reduce the amount of shrinkage, and then of course the subsequent cooling and potential warpage, so that when the part comes out of the mold, you have a good estimate of what the deformed shape is going to be and whether it's still in spec. And this of course can help us predict all sorts of defects along the way, things like weld lines or other visible marks, short shots, in other words, if the mold will even fill in the first place. And on top of that, the warp shape and the residual stresses inside the material, which just like the formed sheet channel that we talked about earlier, can affect the results of a subsequent loading. So again, this is a separate license that can be purchased and added into SOLIDWORKS. And like most of the other simulation tools, there are some different packages to choose from. In this case, SOLIDWORKS Plastics Standard is kind of the basic fill analysis, and it goes up from there. So let's take a quick look at an example of a plastic part that's going to get filled, where we might want to estimate, first of all, if it can be filled on a typical machine, and if there are going to be any issues with deformation or any other kind of defects when we make that part. So let's close down that file and switch over here to my iPhone case. This is a little bit of an outdated iPhone cover, but some of us are old school. I happen to like this version. So just like the other analysis tools, you of course need to start with some geometry, in this case solid geometry if you're talking about SOLIDWORKS Plastics. And again, we would go turn on the relevant add-in. So we'll click the SOLIDWORKS Plastics button, and basically what this entails is creating a mesh, just like most of the other tools that we talk about, defining what type of polymer you want to inject, where it's going to get injected, in other words, where the gate or runner system is in the mold, and then of course simulating the fill and pack process. There is a wizard-like interface that can take you through a lot of those steps, which can speed up the process quite a bit. Again, especially for those of you that may not be as familiar with the injection molding process. And so there are a lot of kind of built-in assumptions, again, that you won't have to tweak if you want to assume sort of a baseline sort of worst case scenario for whether or not your part will fill. If you have a lot of expertise in mold design or running a molding machine, you can go in and tweak all of those properties, you know, the temperature, the flow rate, the material properties, the temperature of the mold, etc. But for this example, let's just take a quick look at whether or not this part will fill. And so of course what we would do to determine that is first create a mesh for the part, which I've already done here. This is what we call a solid mesh, even though the part is very thin. And the benefit there, of course, is being able to simulate more realistically what the mesh looks like and the molten plastic looks like on the insides of the cavity. And we have some special types of elements that are very thin, which help us do that. So this mesh would be set up through sort of a wizard-like interface. And then again, the other basic steps mainly consist of picking your material, which we can choose from a polymer database. You can see here that in the database, we've got about 115 or so different categories of polymers, most of them thermoplastics, but also thermoset materials like silicone rubber or epoxies. And these are real manufacturer grade plastics as well. There's about 5,000 of them, and you can even sort them by company. So if you know that you're using, for example, a BASF material, there, in this case, there are a few hundred of them. And of course, this database allows you to edit those properties or add your own materials from scratch with all the relevant information like the viscosity and PVT curves and everything else that determines what that phase change looks like when your plastic cools into a solid part. So in this case, we're just going to assume that this is a generic ABS plastic case. We've got the material applied there, and really the only other thing we need to worry about is where the gate is. Where are we going to actually inject the molten plastic into the cavity? And there are different ways to represent the gate. You can either just kind of pick a location, or if we want to, we can simulate the flow inside the gate itself if we choose to model some of that in. And that would help us predict things like gate freeze-off, you know, whether or not the material cools too rapidly inside the gate, and maybe, you know, how much waste material we're going to have, how much of it has solidified. So if I were to run this part of the analysis, just the flow in this case, which is simulating how long it takes to fill up that cavity, I can go look at those results and get everything from a simple animation, which I can view kind of on the surfaces of the model, or even in a sort of a cross-section like this. This tells me, of course, how long that the part will take to fill, in this case about half a second. And I can also get an immediate feedback of whether or not this part can be filled and what pressure it will take to fill it. In this case, it's going to require almost 200 megapascals to fill that part. largely because of how thin it is and the material that's been selected. And everything from weld line locations, in this case kind of right after the melt flows around that hole or around the camera lens, potential air trap locations, shear stress or shear rate, which can predict potential surface finish issues in the part. All of these are useful for predicting whether or not there's going to be some sort of visible defect when the part comes out. And so primarily what is often of interest from those types of results, assuming you don't have weld line issues or that those have been resolved, is what is the actual shape of the part and what are the dimensions of the part once that molding process is finished. Depending on what kind of material we're talking about, in many cases it can be difficult to design a mold with the right type of cooling system to keep the mold at the correct temperature so that you don't get warpage. And that's one of the main things as far as what is difficult to predict in the real world. It's one of the main things that SOLIDWORKS Plastics can help with. And so you can see in this example, once we take all of the shear stress and temperature data that was calculated that I just showed you and plug that into the final stage of the simulation, which is called the warpage calculation in SOLIDWORKS Plastics, we can estimate what that final shape is. That, of course, on the left there is an exaggerated shape so that we can see more clearly where the deformation happens. In this case, it's telling me that there might be about 1/4 of a millimeter of shrink. So again, we can figure out if that's not within spec, what kind of changes could we make? Should we add a cooling line? Do we need to change the design of the part itself? Do we need to change the runner layout and how many parts we inject at the same time? So again, we're predicting the initial properties of the part just from the manufacturing process. But similarly to what Tim showed earlier with the C channel, that data can also help us do a more realistic loading analysis. So on the right-hand side, I've done a quick simulation of putting just a force, trying to squeeze the iPhone case, as you probably would do at a basic level in SOLIDWORKS simulation. So in this case, I've done a nonlinear analysis just to make sure that I can handle the larger deflection more accurately if I'm really squeezing that soft plastic hard. And what you see is a comparison of results from top to bottom, where on the top, I simply put that load on and used sort of the built-in material definition inside SOLIDWORKS, which just assumes uniform properties. And on the bottom is where I did the same analysis, but I fed in those residual stresses that were calculated from SOLIDWORKS Plastics and the material properties directly from SOLIDWORKS Plastics. So those of you who have ever tried to do a simulation of a plastic part in SOLIDWORKS may have seen that the library is somewhat limited. There's maybe only 30 materials. This workflow of using SOLIDWORKS Plastics first to simulate the fill now will give you like 5,000 different plastics that you can do stress analysis on. And more importantly than that, they add in those residual stresses and in-mold stresses from the cooling process, which can significantly affect what your real-world usage predicts. In this case, you can see the area of yielding is much larger and the general stresses are much higher overall when you include those effects. So hopefully we've shown you kind of a wide-ranging overview of some of the different types of problems we've helped our customers with and some of the experience that we use to accomplish these things. That as a team, we've got over 40 years of simulation experience, maybe close to 50 now. And part of the reason why we feel that we're effective is that we've learned a lot by working with our large number of customers. We've got over 1,000 customers who use different kinds of analysis tools, everything from FEA and dynamic analysis to flow simulation or plastics. We, as you may have heard earlier, we do consulting analysis projects as well. So several dozen per year. And again, that allows us to sort of get more familiar with very niche industries or specific applications where we can recommend to you what we've seen in the past or what typical assumptions are to get a good conclusion and make the right kind of design choices. So we encourage you to keep track of the content that we put out throughout the year, such as webinars like this, and educate yourself, and then reach out to us if you are interested in going further. And again, we've got lots of examples from the service department that we are happy to talk to you about, and if you're curious as to whether we can help, with your specific application too. So in summary, reach out to us and let us know what you're interested in doing, and if it's a simple, anything from a simple stress analysis to a very complex multi-step manufacturing and loading scenario, we likely have some information to help you out and get you on the right path. This concludes the webinar activity for Simulation Month, so if you've been logging in every week, we appreciate it, and of course, we'll continue to host various webinars throughout the rest of the year, typically on Wednesday. So keep out an eye on the Hawkridge Systems events page for that. Also, if you would like, you can go to the HRS events page and download what we call the Simulation Buyer's Guide as well, which is kind of a text overview of a lot of what we've talked about in this webinar and previous ones. With that, thank you for your time, and if there's any questions, we'll try to follow those up before we conclude. Otherwise, everybody have a good Memorial Day weekend.